So we're going to look at two other example problems here. They're both relatively easy, and the reality is the mean value theorem problem that will probably show up on the exam is not going to be a challenging problem. But again, for some reason, people just really struggle with it. So let's look here. First, we're going to determine if mean value theorem applies if it does, find all points C. So we're going to do two more examples here. So these are actually from the textbook. So this is problem number 15. So we have 7 minus x squared on the interval -1 to 2. And remember, we need to first check to make sure that the mean value theorem applies. Well, f of x is continuous, and we should all know why it's continuous at this point, because it is a polynomial. And then, well, f prime at x is just equal to -2x, which is defined which, remember, defined means differentiable on all real numbers. And it's continuous. I should maybe put here on all real numbers here. You really need to specify where it's continuous in order for us to know that it's continuous on that interval. But we know it's continuous on all real numbers because it's a polynomial. Alright, so mean value theorem applies. Alright, so then the next thing is, remember, there's these steps that I said we should follow. One is to compute f at b minus f at a over b minus a. And so f at b would equal f at 2, which is 7 minus 2 squared, which, if I do my arithmetic correctly, is 3. F at a is equaling to f at -1, which is 7 minus -1 squared, which would be 6. And so f at b minus f at a over b minus a would equal 3 minus 6 over 2 minus -1, which would be -3 over +3, which equals -1. Then the second thing to do is set f prime at x equal to that number. So we need to say f prime at x equals -1. In other words, what we're saying is -2x is equal to -1. And then x equals +1/2. Now, there's only one answer in this case, so we know it's got to be the one that's in the interval, but you should always check, is 1/2 in the interval? Yes, it is. So this is my answer here, is just x equals 1/2. Alright, so let's look at another example here. This is actually number 21. And this problem would show up on the exam, but it would show up most likely in the true or false section here. So 2x to the 1/3 on -8 to 8. So this is, again, we have to determine if the mean value theorem applies. So first off, 2x to 1/3 is continuous on all real numbers because it is defined for all real numbers. That's basically the justification for it. So it's continuous for all real numbers because it's defined for all real numbers. Because remember, this is the cube root, and cube roots of negative numbers are just fine. So then we have to determine if the first derivative is defined for all numbers in the interval. So f prime at x is equal to 2/3 x to the negative 2/3. Now it's not necessary to rewrite this, but I think it's advantageous to do this. So this would be 2/3 times 1 over x to the 2/3 power. Now if you want to take it one step further, you could write this as 2 over 3 cube root of x squared. I don't think it's necessary to do that, but you could do this. Now this has to be defined for all numbers in the interval -8 to 8. But hopefully real quickly you can see that this is not defined for x equals 0. Because if I put x equals 0, if you look at it in just in this part even, you'd be dividing by 0, because x to the 0 to the 2/3 power is still just 0, so you'd have 1 over 0, which is undefined. So what this means is f prime at x is not differentiable for, or not differentiable, not for, on -8 to 8. So mean value theorem does not apply. And this, as I said, would probably show up on a true or false section where I'd say, you know, the mean value theorem applies to f at x equals, 2x to the 1/3 power. And the answer would be false. It doesn't apply to that because it's not differentiable on -8 to 8. So the mean value theorem doesn't apply, and there's actually nothing left to do in the problem. We're done. Because if it doesn't apply, I can't find the point C because I can't use the theorem. All right. Now to finish this section out, there's actually a couple theorems here that aren't really very useful in this section, but they're going to be critical. These are critical for section 4.8. Okay, so let's look at these two theorems here. First one here is theorem. If f at x is differentiable on an interval I, and f prime at x equals 0 on the interval I, then f at x is constant on the interval. Now you might say this is obvious, but what this is actually going backwards on something we already know. We already know that if I have, for instance, f at x equals c, where c is some constant, we know then that f prime at x is equal to 0, because that's what we already know. And it might look like that's what this theorem is stating, but it's actually not stating this. What it's stating is actually the reverse of this. It's stating that first we start with f prime at x equaling 0. So we start with f prime at x equaling 0, then we conclude that f at x has to be some constant. So we're actually going backwards on this. So this is actually kind of the first steps to something we're going to call integration or antiderivatives. And so we're going to need this in section 4.8, as I said. Actually, what we're going to need is we need it for the next theorem here, which is really what we need in 4.8. So let's look at this next theorem here. So if f prime at x equals g prime at x for all x in the interval I, then f at x minus g at x is equal to some constant c for all x in the interval. Well, this is actually really easy to prove. This isn't going to show up on the exam. The proof of this is fairly simple. We start with, we know f prime at x is equal to g prime at x. So f prime at x minus g prime at x equals 0. But then from the previous theorem, which we didn't prove, but it's also an easy one to prove, you actually use the mean value theorem to prove the previous theorem. Previous theorem states that if you have derivatives equaling 0, then we know that f at x minus g at x has to be a constant, because if a derivative is equal to 0, we know that the original function has to just be a constant. Now, what is this useful for? Well, the way we're going to use it in the next section, or in section 4.8, is this is the forward direction. This isn't what the theorem is stating, but for instance, if we're given a function like x squared plus 3, and g at x is equal to x squared plus 5, then we know f prime at x is 2x, and g prime at x is also 2x. Sorry about this. Hit the wrong things there. All right, there we go. So we know that g prime of x is equal to 2x. And so we have the same derivative. So what this theorem is actually basically saying is that since we know that f prime at x equals g prime at x, then f at x minus g at x has to be a constant. Well, and let's just do that here. X squared plus 3, that's f at x, minus x squared plus 5. Well, clearly, if we do this, the x squareds cancel, and you'd be left with 3 minus 5, which is negative 2, which is a constant. So if we get the same derivative, the original functions can only differ by a constant. So as I said, this is actually very important for section 4.8. Alright, so that actually wraps up the section on the mean value theorem. So we're going to do one more video here, and we're going to start section 4.7, which section 4.7 is the last section that we'll be covering. Now, I believe I announced this on Friday, and if I didn't, I'm going to announce it in the video now, and I'm also going to announce it at the beginning of the next video. So we're going to have a quiz on Wednesday, and the quiz on Wednesday is going to be section 4.4 and 4.5 is on the quiz on Wednesday, and you will still be allowed to work in groups.